Having seen 1 and 2 in detail, I'm going to pause and let you work out 3 through 6. If you struggle with these, maybe pause your video and take a look at some of the help videos on the Unit 3 resource page. Don't just guess the answers. I will show you the work to each of these after you submit yours, but it's really important that you're taking ownership of understanding this skill, and it's absolutely a skill that will just get really easy once you've got a critical amount of practice. I expect you to come to class ready to go. Of course, I will answer clarifying questions, but we're going to be moving on. You have to know chain rule. Go for it. Great, so here's number 3. And go ahead and pause if you need to look at the setup. Make a note of where you made a mistake if you made a mistake. Make sure that you understand where this composition comes from and why it's 1/2 right there. And number 4. Same thing, make sure that you understand the setup and each piece of what I wrote. Here's number 5. And this one is worth a couple comments. I put this one specifically here because something funny happens with the derivative of the outside function, which is that the derivative of secant is secant tangent, and there's 2 x's. So if you are going to compose u prime of v of x, if you plug this function into the derivative function, you need to plug 4x plus 1 into both x's, and that's why you see it here, 4x plus 1 and 4x plus 1. And I put the derivative in orange just to help you see that. It's not the original function, it's the derivative of the outside function right there. And then the 4 is the easy part. Here's number 6. Number 6 gets interesting just in the simplifying. The setup shouldn't be too hard. If you looked at this and originally wanted to do a quotient rule, great, no problem. You could have also solved this using the quotient rule and you would get exactly the same answer, and it would probably be about the same amount of work. I just wanted to show you kind of another option. If you're struggling to see why I chose the inside and outside functions that I chose, try composing them. If you plug v of x into u of x, what do you get? You should see that you get f of x, which is why I can think of this using a chain rule. Once I've plugged this in right here, the simplifying with trig, I always kind of hope that something's going to cancel out, and I did actually use an identity. On the bottom, sine squared plus cosine squared is the same thing as 1, so I could rewrite that as 1 plus 2 sine cosine. But ultimately, nothing really canceled on the top, so if you had chosen just to leave your answer in this format after putting the derivative of v on top, that would also be fine as your final answer. All right, pretty exciting. So I want to pause here before we go on to just one more type of example, and remember just the big picture. For example, maybe let's look at number 5. This is a pretty strange function and an even stranger derivative. Think about the meaning of the derivative, and we're actually going to use technology just to confirm that the chain rule is really working, because technically I haven't proven it to you, it's just this trick. One way to show that it's really working is to look at the graphs of the original function and the derivative function, and we should see that telltale relationship between the 2 graphs. So I'm going to pull up Desmos, grab your graphing calculator at the same time. Great, let's take a look. So here's what the secant function looks like. It's got that telltale kind of parabola and then opposite parabola. It's, of course, related to the cosine function. And I'm going to zoom in a little bit because it just is going to allow us to see. If this is our original function, think about what you would expect from the derivative. In particular, notice that we have all of these max and min values periodically repeating. Here's the derivative that we calculated algebraically. What do you see in the derivative that either confirms or suggests that maybe we made a mistake? I'm going to zoom in even further. Right, so hopefully you recognize that the red function derivative has an x-intercept at all of the x values where the original function has a max or min. And you can see that just right here, again here, and of course from the bottom. That's pretty good news. Okay, enough with our graphing interlude. Let's look at some slightly more fun examples. One of the cool things about chain rule, and one of the reasons it's called the chain rule, is sometimes we don't just have a single function composed with another, but we have multiple functions inside of each other. And the chain rule makes it really quick to find their derivatives. Take a look at A. Looking at this expression, can you identify an outside, middle, and inside function? How about now? Right, pretty easy when it's color-coded. So once you get good at the chain rule, you should be able to use the chain rule without writing out u and v and du and dv. It requires that you're really careful, and there's a huge common mistake, which is that people are going to often forget the v prime at the end. But let's try this together, because ultimately you should be quick at this. It's a pretty basic skill. To set up the derivative, I know that the idea is that we're always going to start with the derivative of the outermost function. But then we're going to plug into that outermost function whatever was inside of it, and we're going to multiply it times something else. So the outermost function here is tangent. The derivative of tangent is secant squared. So I'm going to start my derivative with secant squared, but it's not secant squared of x, it's secant squared of something. So I'll leave those parentheses open. Next, what I would do is I would multiply that times the derivative of whatever is inside of it. In this case, what's inside of the secant squared is 5 minus sine of 2x. The derivative of 5 minus sine of something is negative cosine of something. If you think about it, the 5 disappears. And then the last thing I'm always going to do is I'm going to multiply it times the derivative of whatever is on the very inside. In this case, 2x is the very inside. The derivative of that is 2. Now, we do need to plug in what's in the middle. So go back to the beginning here. We took the derivative of the outside. Into the derivative of the outside, we're going to plug in the exact same thing that was in the original function, 5 minus sine of 2x. Next, we took the derivative of what I'm calling the middle function, which is the green function. And that was the derivative of 5 minus sine of something. The derivative was negative cosine. And I'm going to plug into that the same inside function that was plugged into the green function, the 2x right there. This is your derivative. Think of it like links in a chain. This is the first link. It comes from the outermost function, and the inside of it stays the same. This is the second link. It comes from the middle function, and the inside of it stays the same. And this is the last link. It's the smallest link from the smallest inside function, and there's nothing else after that because there's nothing else to compose. There's no x there. There's no inner function. We could rewrite this. I prefer to always put coefficients out front along with any negative symbols, but nothing else is really going to simplify. So here's what I would write. And that would be your final answer. Big mess that it is. Double check that you have all your parentheses together carefully. And then let's take a look at B. Just like before, my first step is to be really careful about what my outside, middle, and inside functions are. And then I start my derivative working from the outside in. The derivative of the natural logarithm is 1 over x. But of course, I'm not going to put in x. I'm going to plug in whatever was originally inside the outside function. So in here, I'm going to put 3 over 2x minus 5 cubed, just exactly like it was up at the top. That's the first link. Second link comes from the middle function. In this case, it might be a little bit hard for you to see what the derivative is. Don't let yourself get distracted by the 2x minus 5. The middle function is 3 divided by something cubed. Well, that's the same thing as 3 times something to the negative 3. And then you just use a power rule. Negative 3 multiplied out front times the 3 is going to be negative 9. And then the exponent is a negative 3, and we drop it down to a negative 4, which is the same thing as saying to the 4th power on the bottom. So it's negative 9 over something to the 4th power. If that was difficult for you, I want you to write the green function off to the side, 3 over x cubed. figure out what the derivative is, and come back and look at this. For those of us who got it, moving on, into this function, I'm going to plug in the same thing that I have, which is 2x minus 5. And then I multiply it times the last link in the chain, which is the derivative of the very insidemost function, which is just 2. From here, there's a bunch of simplifying I can do. I'm going to keep, change, flip on the front, and then hopefully put some things together with the next term. It would look like this. 1 divided by 3 over 2x minus 5 cubed becomes 2x minus 5 cubed over 3. And then I cancel out 3 of these binomials with 3 of them on the bottom because they are exactly the same, which leaves me just 2x minus 5 on the bottom. And then I simplified negative 9 and 3 to be negative 3 and multiplied times 2. That's where the negative 6 comes from. And that's the derivative, which is actually a very simple derivative for what seemed like a pretty complicated function at first. Pretty fun. You've got 3 to do. Go ahead and work out these 3. Be really careful about your insides, outsides, and middle functions. When you press play, I'll show you the answers. Great. Here are the answers to 1 and 2. Pause if you need more time to look at them. And here's number 3. That'll be it for today. See you in class.